All right. All right. Hello, everyone. My name is Nathaniel Hudson. I'm a postdoctoral scholar here at the University of Chicago, working under Kyle Chard and Ian Foster. And I'm here to talk about Flox, Federated Learning on Globus Compute. So to start, I want to give a high-level introduction to what federated learning is, kind of following up on what Matt was talking about earlier. But to start, I'm going to talk about data. So in order to do any type of AI workflow, you have to have a lot of data. The pile is a very famous data set for textual data, and it's very large. It is 800 gigabytes in size, and even despite that, relative to other AI data sets, it's actually relatively small. So this is what I like to refer to as the big data problem. We have so many decentralized devices, from smartphones, wearables, sensors, and personal computing devices, let alone all of the other infrastructure like the APS at Argonne, that generates large amounts of data each and every day. Roughly 330 million terabytes of data are generated daily. So how do we transform those large amounts of decentralized data into actionable knowledge? It's challenging. The conventional approach would be, hey, let's take that data from the data owners and offload them to some centralized training infrastructure, whether that be Aurora at the ALCF or AWS or some other cloud infrastructure. The problem is you can't reliably transfer 330 million terabytes of data over the network. That's just infeasible, it's impractical. Not all of the data are going to be good, so we can't do that. So federated learning, which was originally proposed by Google back in 2016, has arose as a really popular and ideal alternative to this. So instead of relying on these data owners communicating their data across the network to some centralized location to do the AI training, instead, this centralized location, which we'll call an aggregation server, will share the model to the data owners, where they will then do local training on their data without ever having to communicate it across the network. And then periodically, the locally updated models are then communicated to the aggregation server, which then fuses them through aggregation. And then this is just a continual loop where you have continual updates flowing through the network. And there are some immediate benefits to this approach. One, you have an immediate layer of data privacy, because if you have private sensitive data, it's not going over the network. Additionally, the communication cost reduction are enormous. So with that being said, we're looking in, one of the things that we did last year was publish a paper on Flox, where we essentially implement a framework that implements federated learning using Globus Compute as the network infrastructure, where you can register each of your devices or data owners, whether that be an IoT device, personal computing device, or an HPC node. As long as it's a Globus Compute endpoint, you can launch local training jobs on those endpoints, and it will orchestrate all of the communication between your endpoints and your aggregation node. Now, even though Flox is great, and there are other great federated learning frameworks that exist out in the wild, there is a problem. Flox and other FL frameworks do not natively support what we like to call hierarchical networks. And so the reason why this is important is because IoT networks are not nice and staggered, where you have one centralized server and a flat layer of decentralized devices. And in fact, we have an ongoing collaboration with Dr. Shalisa Sohail and Dr. Melanie Oye from the Universities of Newcastle and the University of Waikato, where they're wanting to deploy these sensors and these gateways to rural applications, so growing tomatoes and then other types of problems. And there's a natural hierarchy here. So you have a topmost server, some intermediary devices, and then the bottommost gateways. So we argue that federated learning frameworks need to have hierarchical systems, and they need to consider, they need to also support local simulation for rapid research ideation and algorithm development, and they need to be compatible with edge devices and HPC systems. And we are doing a complete rewrite of Flox in order to support these workflows. So for the sake of time and for the sake of avoiding errors, I'm going to show Flox 2.0 in action, but not as a live demo. So in order to use this rewritten version of Flox, you need three key things. One, you need what we call a Flock network, which is essentially just the definition of your network of data owners. Two, you need a federated data set. And three, a deep learning model to train. Now, we're not going to reinvent the wheel in terms of how to create these deep neural networks. We're just going to build on top of PyTorch and PyTorch Lightning and come up with some nice convenient wrappers for us to use. Now, for defining a flock, we want this to be as simple as possible. We use just a simple YAML file where you have each of your nodes are enumerated. You denote what kind of node it is, whether it's a leader, an aggregator, or a worker, i.e. the nodes that are actually doing the training. You give them a Globus compute endpoint, and you give them a proxy store endpoint, and that's it. And using this YAML file, in Flox, what you can do is you can just simply use the Flock object and then import it from the YAML object, and then immediately you have your network. So we want it to be simple and easy to define these networks. Additionally, for rapid prototyping, if you're a machine learning researcher and you want to come up with new FL algorithms that handle things like diverse data really well, we have what we call federated data sets. So first, a lot of data in machine learning are naturally centralized. You just have a big clump of data samples. So we're going to take fashion MNIST, and we're going to use this function that we created called federated split, which takes the centralized data, it takes the Flock network that we defined earlier, and then it uses what we call these alpha parameters, which are drawn from the Dirichlet distribution. You can kind of think of it as popularity of each item. So using this, we can immediately and very quickly come up with really heterogeneous or homogeneous data distributions across the workers. So this is really nice if you were someone like Matt, who is investigating some of the trade-offs associated with the data distribution across the endpoints. And then finally, once you have all of these things together, you just have to call federated fit. It takes in the Flock network, the module that you have written that you want to train, the federated data set, and some hyperparameters like the number of global rounds, the strategy or FL algorithm you want to run on, and once you call it, it will do the simulation and give you the results. But one thing I want to point out is that we have this nice little argument called where. With the Flock network definition that I showed earlier, because it has those Globus compute endpoints, in order to go from a local simulation to actually launching it and executing it on these remote endpoints, all you have to do is change this where equal local to where equal Globus compute. And immediately, all of the headache of actually setting up the network and the infrastructure is done and handled for you. And in closing, Flox is currently closed source. We're hoping we just want it to be up and ready to go with as little breaking changes as possible once it's launched. But feel free to contact me if you have any questions, because we're hoping to roll it out very soon. And then thank you. Let me know if you have any questions. And I just want to give a shout out to some of the other collaborators who have helped me brainstorm ideas of what this should look like in terms of software and whatnot. And yeah.
So you also use Globus compute multiple in Globus compute endpoint. How do you share them? You also like register through Globus support?
So each of the endpoints will be a separate Globus compute endpoint. So it's not like we're sharing them with multiple users. So I think, and correct me if I'm wrong, you're asking this from the perspective of Appful, is that?
Yes.
Yeah. So with Appful is a cross-silo FL platform. Flox is more of a cross-device FL platform. So we're assuming that your devices are all owned by one person rather than you have multiple hospitals that are wanting to join one single federation, and they're very, very, very disjoint from one another. So that's kind of a difference in perspective, because we're assuming that everybody owns their Globus compute endpoints. So there isn't the issue of multiple users.
So how you send tasks to different endpoints?
So like essentially Flox will essentially launch a single local training job to each of the endpoints separately. So they're training independently from one another.
The big difference is we're not running on HPC. So the problem is we cannot share. Generally speaking, we're not allowed to share endpoints on like ALC because it's against all of the policies that ALCF has in place, same at NOAA, same at all of these big facilities. The work that Nathaniel is doing is running on Raspberry Pis that live on a farm. There are no such legal requirements that stop us sharing access to those. So it's a really big use cases, make it a lot easier for us in terms of sharing.
All right. Thank you.